Hello everyone, this is lecture 12 of course BE544. In the previous couple of lectures we have learned how to deal with simple CNNs and pre-trained models by applying manual configurations or hyperparameters and then optimizing the hyperparameters using two frameworks, namely Keras Tuner and Optina. In today's lecture we will go through a new approach and a state-of-the-art design called vision transformers. Vision transformers have emerged as a groundbreaking approach in the field of computer vision, offering an alternative approach to traditional CNNs. Vision transformers inherit and utilize the principles of the transformer architecture, which was originally developed for natural language processing. Practically, vision transformers have demonstrated exceptional performance in various vision-related applications such as medical image analysis. The traditional and original transformer architecture introduced by Vaswani et al. In 2017 revolutionized the field of natural language processing as mentioned, with its ability to model long-range dependencies and its scalability. The core concept and component of a transformer is something called self-attention mechanism. The self-attention mechanism will allow the model to weigh the importance of different parts of the input data relative to each other. Based on the self-attention mechanism and cascading multiple of them together, this led to the development of vision transformers. In 2021, the vision transformer model was introduced in a research study called An Image is Worth 16 by 16 Words Transformers for Image Recognition at Scale. As mentioned, vision transformers is inspired by the success of transformers in natural language processing. In natural language processing, we are dealing with sentences and paragraphs and words. Vision transformers got that concept and introduced it in a novel approach to image analysis by simply partitioning images into smaller batches and employing self-attention mechanisms. So instead of dealing with the image as a whole, we are dealing with images as smaller batches. And as noted in natural language processing, we are dealing with words or vectors, so images are converted into vectors to be used with a self-attention mechanism. Vision transformers can capture both local and global relationships within the image, and based on that, it became a remarkable approach in many tasks and fields such as medical image analysis. In their study, they noted that in the abstract, that the vision transformer attains excellent results compared to the state-of-the-art CNNs while requiring fewer computational resources to train. And they noted also, they showed that the reliance on CNNs is not necessary, and a pure transformer applied directly to sequences of images or image batches can perform very well on image classification tasks. And this is their proposed architecture and model of the vision transformer. And we are going to illustrate each part of it in this lecture. First, the image is converted to smaller batches and then converted to embedding and something called position embedding, and the position is added with the embedding to become position embedding, and then they are subjected to a set of encoders and then to a classification head, and finally the output is retrieved. So let's start a step by step. In the first step, vision transformers divide the input image into fixed size and non-overlapping batches. So if we have an image like that, the vision transformers will split it into smaller batches. This is similar to splitting a sentence into words in natural language processing. As mentioned, vision transformers inherit the concept of the original and traditional transformers. So if we have an image with a size, width and height and number of channels C, and the vision transformer required to divide it into a batch size of P multiplied by P, so the number of batches in a single image will be H multiplied by W divided by p square. Each patch, noted as xi, is flattened into a vector, so the size of this vector will be p square multiplied by c, which is the number of its channels. So now we have n batches, each sized of p square multiplied by c. After splitting the image into smaller batches, positional encodings are explicitly added to the batch embeddings. This is because to preserve the spatial information and relationships between the batches. So each batch can get a number, for example, this 1, this 2, this 3, 4, and so on. This step is crucial because the architecture is invariant to the order of the input sequences. So the order is added explicitly to the batch embeddings. Another reason, these embeddings will help the model to understand the relative position of each batch within the image, aiming to ensure that the spatial relationships are captured inside that image locally and globally. So if you have a vector which is flattened that present a patch, a position encoding is added to it to become a new vector zi bar. After the division process and batch embedding, a spatial token is added, which is called a spatial classification token or CLS. This token is prepended at the beginning of the sequence of batch embeddings before feeding them into the transformer encoder, which is the next step. This token will interact with all other batches through the self-attention in the encoder and will aggregate the information from the entire image. And the final hidden state will be used for the classification task. So the CLS token will be used later in the classification as noted here in this process. So now we are here and we have position embeddings and batch embeddings, and CLS is prepended to that sequence. Now all of that will be subjected to the transformer encoder, and this is the internal structure of the transformer encoder. It starts by accepting the embedded batches and encodes them to get an output. So the core of the vision transformer encoder is found in two primary sublayers. The first is called multi-head self-attention, and the second is feed-forward neural network, which is here and here. In the encoder, there is also the add and normalization layers. Each of them has a specific task, but mainly this encoder is repeated multiple times, for example n times, in a sequenced manner. This means we have embedded batches is subjected to an encoder, and then the output of the first encoder is an input for the second encoder, and so on until we reach the last encoder that will be subjected to the classification head and then to the classification output. So now we have n encoders, and the sequential stacking is crucial to the architecture's ability to build increasingly complex representations of the input data. And the hypothesis behind that is that different learned representations can improve the overall transformer performance. So now we have embedded batches, which is applied to a sequenced manner of encoders, and each encoder will contain the same components. The first component is the multi-head attention. Inside the multi-head attention, something called self-attention mechanism. The self-attention mechanism captures the relationships between different inputs, which are the batches in the input sequence. For each batch or batch embedding, the self-attention will compute a weighted sum of all batch embeddings with weights determined by the relevance of each batch to the current one. By doing that, this mechanism will allow the model to focus on important batches while considering both local and global contexts. Talking visually in the right figure, if we have a figure like that or an input like that, the attention means you are focusing on some parts of the images or a set of batches, if you are splitting that into batches, and then it will focus in a set of batches more than others by adding more weights to some batches than other batches. So the multi-head attention will involve applying the self-attention mechanism several times in parallel with different linear projections, where each head of the parallel heads will process the same input simultaneously but independently, capturing different aspects of the relationships between the input data, which are the batches. So now we have embedded batches, or the input is provided to the multi-head attention. Each of them will capture different aspects of the relationships, and after that they will be provided to a multi-layer perceptron or a feed-forward network. So after the multi-head attention, each batch representation is processed through a position-wise feed-forward network. Using the FFN or the feed-forward network will introduce some non-linearity and enhance the model's capacity to learn complex patterns. The FFN or the feed-forward network will operate independently on each token or element, and internally it consists of two linear transformations with a ReLU activation between them. So now the role of the encoder is to extract the relationships between the input data, talking about the batches, and then introducing some nonlinearity to learn the complex patterns between the batches, and the encoder will be provided to another encoder, and so on until it reaches to the classification head or the output layer. So the classification head is the final component that will process the learned representations from the transformer encoders to produce the classification predictions. Internally, it consists of a sequence of operations designed to aggregate the learned features and output the class probabilities. As noted from a while, a special token, which is named CLS, was added to the sequence of batch embeddings, and this token is intended to aggregate information from all batches to make the final classification. And during the training process, the model will learn to use the representation of the CLS token for the classification task. The input sequence, including the CLS token and the batch embeddings, is processed by a series of transformer encoder layers as mentioned. Each encoder layer consists of multi-head self-attention mechanisms that work in parallel, followed by feed-forward networks, layer normalization, and residual connections. After the sequence has passed through the transformer encoders, which work sequentially, a final normalization layer is applied to stabilize the outputs. To get the classification output, the CLS token is extracted from the final normalized output sequence. Then, this token embedding is then passed through a fully connected layer to transform it into the class scores, and then the logits are passed through a softmax function to produce the class probabilities. Back to the figure again. Now we have an image that's converted into patches that are projected and flattened, and then the position is added and the CLS token is added or prepended. Then all of that sequence is encoded in a sequential manner using N encoders, and then this is subjected to an MLP head, which will extract the prepended token after being encoded and learn it to represent the output, and this extracted token is applied to some processing until it reaches to return the logits, and these logits will be applied to a softmax function to produce the class probabilities, and based on these probabilities you can obtain the class. To go deeper in understanding the vision transformers, we can talk mathematically. So let's consider an input sequence of embeddings Z with this vector Z1 bar, Z2 bar until we reach Zn bar. And Z1 bar, as seen here, it's the batch added to the position. And the dimension of Z will be N multiplied by D model, where N is the number of tokens or batches and D model is the dimensionality of the embeddings. So we can say the embeddings or the size of the embedding of each token or batch, for example 100 or 1000. Then the queries Q, keys K, and values V, which represent the linear transformation or projections of the input embeddings, can be computed as presented below. And Q, K, and V are the inputs to the multi-head attention. If you notice here, there are 3 inputs, which represent the queries, keys, and values. To compute the Q, we multiply Z, which is the embedding or the input sequence of embedding, by WQ, and the same for keys and values, where WQ, WK, and WV are learnable matrices that will be tuned in the training process. And the dimensional of each will be the model multiplied by dk, where dk is the dimensionality of the key vectors. Now we have q, k, and v, which are the inputs to the multi-head attention, and it's worth noting that each of them is computed independently. And if we have multi-head attention, as mentioned, we have parallel multi-heads. This means each q, k, and v is computed independently for each head. Now, if we have multiple heads denoted by h head, so for each head or for each attention head I from 1 to h, you are required to compute q, k, and v for each of them. So if you have 5 heads, you will obtain 5 q's, 5 k's, and 5 v's. Each is computed independently. After that, to apply the attention mechanism, you go for each head I and compute the scaled dot product attention as presented in this equation. You are applying q dot product to k transpose divided by the square root of dk, and then you apply softmax, and then you multiply it using dot product by v. And this will be the attention of q, k, and v. By doing that, this will result in the attention output for each head I, which is represented by head I will be attention of q, k, and v. Now you have h heads, then you will concatenate all of them together by putting each of them together, and this will result in a matrix of size n multiplied by h dot product of dv, where dv is the dimensionality of the values. After the concatenation, you will apply a final linear transformation to the concatenated outputs. This transformation will project the concatenated matrix back to the original model dimensionality, which is the model, by simply multiplying using dot product by WO, and WO is another trainable weight matrix. So for the multi-head attention, we can get a matrix called multi-head of q, k, and v. Then you will find in the architecture that the input is used twice. First is normalized and then provided to get q, k, and v, and then another path here is added to the output of the multi-head attention, and this is called normalization with residual connections. And the aim for that is to stabilize the training and improve the gradient flow. After that, the output after the addition operation will be provided again here to another normalization with a residual connection, and the output of the normalization is provided to an MLP layer, which is called feed-forward network. This feed-forward network will consist of 2 linear layers and a ReLU function between them. And this is simply presented by x, which is the output here, x and x, or simply after the normalization, x here, multiplied by w plus the bias. W is the weight, p is the bias, and then for the first layer, a ReLU activation function is applied, then the output is multiplied again by W, which is the weight or the second weight, and added to the second bias. And the output of the second layer, which is this, or simply FFN of X, has the same dimensionality as the input, which is the D model. And the introduction of the activation function ReLU will introduce the nonlinearity that will enable the network to learn nonlinear transformations of the input data. Again, the normalization and the residual network here will stabilize training and improve the gradient flow. And the normalization layers here and here will normalize the input to have a zero mean and a unit variance, which also will help to stabilize the training process. After that, this will be the output of the encoder. The output of the encoder is applied to another encoder, to a third encoder, and so on until it reaches to the classification head and then to the output. So remember that the class token is added initially or prepended to the sequence of embedding Z as presented here. And after the encoding, we need to extract it. So the CLS token is extracted from the final normalized output from the beginning because initially we prepended it to the sequence of embeddings. So ZCLS will contain the aggregated information necessary for the classification. After that, this token embedding is then passed through a fully connected layer to transform it into the class scores by simply multiplying it to a weight plus bias, and both of them are trainable. By doing that, we will get the logits. Finally, the logits are passed through a softmax function to produce the class probabilities as presented in this equation. And the softmax function will get a probability for each class, and to get the corresponding class, for example, benign or tumor, we need to find the maximum index of them, and based on the maximum index, we reflect it to get the corresponding class. So for example, if we have 0.7, 0.2, and 0.1, this means that the first index is the class or the corresponding class. So you get the corresponding class that reflects the index 0, and this will be the prediction. Again, visually, the image is divided into patches and then flattened, prepended the class, and then embeddings are subjected to a set of encoders, then to the multi-head, and then to the class output. After understanding the vision transformer, now we can compare between vision transformer and CNNs. The vision transformers utilize self-attention for features extraction and global context modeling, while the CNNs applies conv and pooling layers. For the vision transformers, the image is divided into patches with fixed size and non-overlapping, while CNNs deals with the pixels and reduces the dimensionality using the pooling layers to extract the local features. And talking about the global context, the vision transformers captures it and captures the global relationships from the beginning, while CNNs captures local and some global context through hierarchical feature extraction through cascading, conv, and pooling layers. Vision transformers require more data than CNNs. CNNs can work with fewer data. And this is another simple comparison between ViT or vision transformers and CNNs. So in this lecture, we have dealt with vision transformers, understood the meaning behind it and the theory behind it, discussed the different components that begins by splitting the image into batches and then embedding it and prepending the class token and then applying the encoder or multiple cascaded encoders sequentially and then applying the classification head that will provide the logits and then will be applied to the softmax function and finally getting the prediction. We discussed it also using mathematical notation to understand the process behind the scene. Finally, we have made a comparison with vision transformers and CNNs and we can conclude that vision transformers compared to CNN can be more efficient if we have enough data. And finally, we can conclude that depending on the application of itself and the task in hand, we can decide whether to depend on the vision transformers or CNNs. Moreover, we can test each of them individually, and based on the performance, we can decide if the vision transformers or CNNs can fit to this task in hand or not.